Dominic to introduce the next session.
Yeah, superb. Thanks, Val. So we've just a couple of housekeeping notes before we kind of jump into the next session, which is going to focus on fuel cell technology advances and the impact on aviation's roadmap. We've been running polls. You'll have seen the first poll go live, and there'll be a number of these throughout each session. So do respond and give us your thoughts. Also, if you want to add something more qualitative, give us your thoughts in the chat function or on anything that the speakers are talking about. Feel free to comment and put your own thoughts across. If you have a specific question for the speakers, please put that in the Q&A function, because that's where our moderator will draw from. And then just to kind of finish off on our first poll that we've run, we've seen quite an interesting response. So a third of participants think that hydrogen can contribute more than 50% of the carbon emission and greenhouse gas emission reductions before 2050, which is great. Now, my wife's an academic, so I'm aware that this is possibly a hydrogen aviation summit. It might be a bias sample, but I think when you look at many of the roadmaps and targets, we can see that it's people where we've got to those published, it's a far lower percentage that people are looking at. So in the Jet Zero strategy, for example. So really interesting to hear those thoughts from our audience. So yeah, very quickly, we're just about to bring in our panelists for the next session. Just another quick thing to note, after this session, we'll take a short break, 5 minutes, and then we will come back after that, and we'll start again with panel session 2. So very quickly, just jumping in for the panel session 1. So fuel cell technology advances and the impact of aviation's roadmap. So we're fortunate to have a great panel. Unfortunately, we've lost a couple of the panelists we initially had. So our moderator, Rob from H2View, is unable to join, unfortunately. So I think you're going to be stuck with me as the moderator, but we'll try and get through that. And unfortunately, Rudolph from our team is unwell. So like all great sports coaches, it's about when you make a substitution at the right time. And I fortunately collared Val and brought him into this session as well. So he'll be able to comment on some of our fuel cell development and where we see the roadmap ahead. So as an introduction to this session, so in 2023, this year, we've witnessed some world first breakthroughs in flight, which we outlined at the start of the panel session and at the start of the conference. We've seen increasing confidence in the timeline. We've seen investors come in and we've seen commercial deals continue. We've had these eye-catching moments of aviation history, but behind all that, behind the scenes, what we're seeing is rapid advances in the fuel cell technology, things that we've seen and the Department of Energy have seen over 20, 30 years. Those continue, and there's great optimism about the technology. So hopefully we're going to hear some of that today. And we also might hear a little bit about some of the challenges. So this session is really looking at those breakthroughs, looking at where our panelists see the things heading in the future. And so just to quickly introduce our superb panel, we've got Merrill Mallory, who is VP of Engineering for Plug Power. Merrill has 25 years of engineering experience, roles up to leadership in engineering at Ensign Bickford, and has been with Plug Power for a number of years as well. And then we also have Lisa Karlhammer, who is SVP of Engineering at PowerCell. And PowerCell, as many know, are a supplier of fuel cells to ZeroAvia. And Plug Power also, of course, had their fuel cells in flight, as I mentioned earlier this year. So relevant products that are actually in the air flying, powering aircraft. And as our third panelist, who is going to join me just to the left-hand side here, is Val Miftakhov, our CEO and founder. So Val, if you want to come into the frame as well, and we'll kick off if that's all right. Okay, so I'm going to start first with Merrill. Really, what we'd love to hear you start and cover is what is the roadmap? Where have you seen fuel cell development come from? How are we tackling challenges like thermal management, like the weight of the systems? And what's your kind of prediction and thoughts about where the technology will head over the next couple of years? And then we'll throw over to Lisa, and then we'll bring in Val.
Okay, so fuel cell technology is making leaps and bounds as we've been talking about, and Plug's been working on several areas of technology in the fuel cell realm, looking at reducing rate, specifically related to our ProGen engines. 125 kilowatt is looking at how we're going to reduce weight within the fuel cell itself, also improve durability, and also look at the ability to do high temperature operation. So a few things in those areas that we're working on to drive specific power increases. As we know, weight is really, really critical for aviation technology. So how are we taking the weight out of the systems is something that we're thinking very seriously about. One way to do that is look at the fuel cell plate itself and reducing weight. Another thing that we're looking at is evaluating higher temperature operation, as I said, which is going to help with reducing the weight of the heat exchangers in the systems. Roadmap areas are also looking at durability of the MEA itself. The aviation industry wants long life, as does on-road applications. So figuring out a way to reduce the life of the MEAs through looking at our catalyst and our catalyst technology, which is really good for aviation because the cost that we can incur in aviation is much higher than we can on-road. So we can afford more catalysts. What else would you like me to address offhand, Dominic?
Yeah, I think it would be great for us to, and we'll get into some Q&A in a little bit, but Meryl, it would be great just to hear a little bit more about some of the projects that you're working on, as much as you can kind of share with the audience at Plug, and then maybe a little bit around the experience of working with partners to have the fuel cells in flight earlier in the year.
I think the one thing I'd like to really mention about Plug Power is we're working on the end-to-end green hydrogen economy. So we're not just working on fuel cells, we're really working on projects and electrolyzers to generate hydrogen. So we're not only producing hydrogen at our company, we're doing storage solutions, we're working on delivery of hydrogen, and then we're looking at how we're using hydrogen in our end-use applications. We've built the first viable market for hydrogen and material handling, really to support operations of our customers like Walmart, Amazon, Home Depot. So many advances for material handling and how we're applying fuel cells to forklift applications. We're also continuing to invest in innovation through our joint ventures, many of which are centered on transportation. And as a part of that transportation industry, beyond just the road, we have several partners that we've developed in the aviation space, which includes a company that we acquired in 2019 called Energy Ore. And we've become a leader through that acquisition in UAVs and aerospace. And we've set several world records for endurance flights through some of our proprietary fuel cell technology. But most recently and most exciting, we designed and manufactured the ProGen fuel cell that made aviation history with the universal hydrogen flight that we showed earlier in the broadcast. And it was exciting for us to see our ProGens in work for that particular flight and knowing that we've made a difference. We also have partnerships with Airbus and are working to implement hydrogen in our air travel applications with them. And we have a partnership with Aviation in France with Renault, where we're working on transportation fuel cells for light commercial vans. Terrific. And I can get into whatever more details you'd like to hear, but that's kind of
we'll dive into a bit of conversation as well in a little bit, so we'll get some questions. But yeah, so really just the kind of same question to you, Lisa, and then we'll throw it to Val. So where have we been over the last 5-10 years, particularly in the context of the underlying performance of fuel cells and what makes it more and more relevant to commercial aviation? And where are we going? Where are we headed? And what is PowerCell doing, and what's your approach?
Yeah. Thank you for inviting me here first, I would like to say. I'm really excited to be part of this. And I was thinking a little bit, reflecting fuel cell and advances on the impact of the roadmap for aviation, and what highlights and key innovations to pinpoint here today. And I realized that the innovation process for having something for aviation for the future started many years ago. For me and for PowerCell, it was I think it was the development of the P-stack that changed my view on the possibilities for fuel cell technology. And before that, we talked about 5 kilowatt systems for portable applications and for range extenders. But after that development, we talked about full propulsions for vehicles and also for aviation. And as we have seen, it has been up flying with your solution some time ago. At the moment, we are developing a new platform where we inject all the learnings from all these building blocks that we have utilized over the years, but with aviation in mind already from start. This project was kicked off within this European funded newborn project, but we have a lot of other activities also in parallel, because I think it's important to get the learnings from usage and also from already now talking about what's important for the certification process for the future. And I see it as an iterative process, starting up with a P-stack in the air, get the learnings from that, tweaking everything a little bit for the next generation. As Meryl talked about, weight is of course very important for aviation, but also operating temperatures to be able to minimize the weight of the complete system. Volume is always important in every application, but also understanding max power and if we can tweak a little bit on the max power and max current output. And I see that we will not end here, and we don't really know where we will end either, because it's a continuous improvement of the characteristics of a fuel cell stack, as I see it. Learnings, improvements, learnings, improvements.
Mm-hmm. Yeah, I agree with you when you talk about getting the fuel cells out there, getting use, in industry, because that's the best way we're going to learn. I mean, that's one of the reasons why we entered the material handling market, was getting our fuel cells. We have about 60,000 fuel cells in operation and material handling right now, and you get all that collective data back on how they're performing. It really makes a difference. So the more the fuel cells we can get flying, the better off we're going to be. That's no doubt.
Fantastic. It's not that dissimilar to how we think about our overall powertrain as well, getting this flying with small aircraft first, and it gives us the opportunity to scale and grow it into larger platforms over time. So Val, exactly the same question to you, I think, is where do you see, I mean, we talked about limitations a little bit, and Lisa saying, we can keep progressing. Where have we been? We were actually showing some guests around earlier, and we were looking at the fuel cell system that went to the power generation system that went into our Piper Malibu, and then looking literally across to the Dornier, and so you can see that step change in amount of power we're generating with fuel cell power generation. So where have we been? Where are we headed? And what are really the next big exciting projects that we're working on?
Yeah, thanks, Tom. And I'll try to do the subject justice, given that Rudolf was not able to participate. It's a cold season, I guess, here in the UK, and we have some fallen comrades here. But on our side, so we started the journey, of course, back 6 years ago when we started the company, and early on we have engaged with a number of fuel cell manufacturers and ultimately selected PowerCell for our initial prototypes, and then now also for the first production version of our 600 kilowatt engine. And if you look at our prototypes over time, we have flown a number of different systems. Progressing the system design around the fuel cell stacks. Every iteration of the system is more advanced in terms of the control capabilities, measurement capabilities. Now we're bringing in the final iteration of the design that will be a certifiable version of the power plants that we're actually about to submit for certification with the authorities. And that has a very integrated balance of plant system, highly redundant super stack structure, as we call it, that brings in the redundancy in the fuel cell stack operation, but also in the balance of plants, in the power distribution, so that there is no single point of failure in the system, or at least no single point of failure with new technologies in it, because you can have single points of failure which are quite reliable mechanical components, but you don't want to have it in the new technology domain. And we've been pretty fortunate to be able to progress the power density, energy density, the temperature of operation, and the control characteristics of all these systems in partnership with PowerCell. So that's been great. We also have, of course, in-house development of the high temperature fuel cells that are based on a completely different membrane, electrolyte, bipolar plate design approach. We, to our knowledge, were first in the world that we were able to make aluminum bipolar plates working in the highly corrosive, high temperature PEM environments that was enabled by our unique coating development that we did in-house initially with our partner, longtime partner, High Point, and then, of course, now part of the company, part of ZeroAvia in our Sandwich, Kent location here in the UK. So there, we believe that high temperature fuel cells are the unlocking technology for large aircraft development. So when you think about 20 seats and above, basically Part 25 aircraft, we think that going to those temperatures and beyond becomes a requirement. We have demonstrated our fuel cell, high temperature fuel cell systems, pressurized systems, operational at up to 200 degrees Celsius operation for thousands of hours, looking at the degradation rates and all that. And this is just the beginning. Of course, we are going to also fly. We believe we're going to be the first to fly high temperature fuel cells next year in the manned aircraft. So that will be quite an important milestone for the industry, I think, overall, both for fuel cell industry and for the aviation industry. And we're looking to work further on developing that technology into higher power levels with the cell sizes and stack sizes, but also some developments on the membrane technology that we're doing together with BASF, and MEA development, and some of the balance of plant development as well. So higher temperatures allow you to not only simplify the cooling systems, but also allow you to move potentially from the liquid cooled to air cooled cooling approach, eliminate the need for intercooling post compression, enable higher compression ratios, which means that power density can increase even further, and you can operate with higher pressures in the chamber, which has been traditionally for turbine engines, for traditional engines, temperature and pressure was the name of the game for the last 50, 60 years throughout the market. As we got now, we believe, to diminishing returns on the combustion technology, we've run out of materials in the cooling approaches, so the engine cores literally melt. Now we're resetting that cycle, and the cycle goes from the automotive sort of sub 100 to now 200C and then beyond. So exciting times ahead. Hopefully that's a good enough for a summary.
good. It's a great overview. So we got some great audience questions coming in actually. So I'm gonna jump in straight into some of our audience questions. And the first of those I wanted to flag up was from James Hunt. He asks, durability presumably increasingly an issue. At what point do we move to composite bipolar plates? So I'm curious, does anyone have any thoughts on the need and urgency of using composite bipolar plates? Maybe first I could address that to Meryl. Is that something you've looked at?
So we've looked at a different plate technology from metal, but we haven't gone and looked at a composite material. If you're, when the person's asking about composite, what kind of composite materials are you looking at? We're asking about, would be my question. Zach, does he have an answer to that? Because we're not looking at a composite material. We are looking at alternate materials to metal. That's all I can tell you. But
So
that's a long
Lisa,
way. That's a long ways out. That's not next year technology for us. That would be several years out.
So Lisa, any thoughts on that question in particular?
I think it depends a little bit on what temperatures you are aiming for at high temperatures, because we don't really see an issue continuously using stainless steel up to, I don't know, 120 degrees or so. But if you want to also reduce weight, you need to have a look on different materials, maybe depending on what solutions you find, but we don't see a problem with stainless steel up to that temperatures.
Jonathan, you want to come in on the plates?
I think there was also an aspect of the question on the durability side as well. Yeah, so that's how they look. So durability separately is a big topic, of course, and you know, if you compare the durability of the fuel cells, starting with low temperature fuel cells with the aviation technology, with especially small turbines, the fuel cells win easily. Yeah, so we have fuel cells like PowerCell, for example, and others that are used in the heavy duty environments with tens of thousands of hours, 10,000 hour plus durabilities, and which is relatively unheard of in the small engine space, at least in aviation. So a typical small turbine, which is used to power aircraft that you see on our background here, and up to 20 seats aircraft, Pratt & Whitney PT6 has a 2,000 hour or less hot section inspection and 4,000 hours or less complete overhaul of the engine. So having the 10,000 hour, 20,000 hour fuel cell there is a huge benefit on the maintenance costs and durability. On the composite separately, we are quite interested in that from the high temperature side of things. And that's mostly driven by a little bit by weight considerations, because aviation is very weight sensitive, but also by formability, right? As you try to get as much current density and as much reagent flow, how you form your channels, how you integrate the cooling channels, the gas channels, and all of that topology together, especially with when you deal with gases all around, both for cooling and for reagents, the formability becomes an issue. And with composites, you can theoretically do better. So those are some of the areas of interest for us.
And Meryl, you wanted to come in there, you had a comment.
Yeah, I just wanted to ask about, because we're hearing targets of past 10,000 hours really being needed for aviation, looking at the 27,000 hour durability target. I think looking at the MEA itself is also really important, and how the materials of the MEA are going to affect the durability. Are you looking into that as well on your side?
On our side, absolutely. Yeah, I think the holy grail, I guess, is to get the power plants to the level of reliability or the time between overhauls of the aircraft, which would be this 30,000 hour type situation, right? I don't think that's a requirement for the market. The requirement is exceed the current solutions, right? Which for small aircraft is relatively easy. I mean, relatively, nothing is easy about aviation, but relatively easy for fuel cells. And then as we go larger and larger, that's when additional pressure on the hours starts creeping in.
Lisa, anything to add on that conversation? I mean, is durability something that you're looking at very closely, and are there any other pathways that you see to improving durability?
Who are not looking into durability, but it's all a question about durability is so tightly connected to how you operate your stack as well. And as you all know, fuel cell technology can be killed by a few seconds if you're doing something really stupid, and you can make it last for 10, 20,000 hours plus. But I think that it's all about all the details that needs to be tweaked a little bit. If you want to run at a higher power density, at higher temperatures, of course, that will influence the stability of the noble metals. That is something you need to work on. Also, the membrane technology is something that we need to work on, and has already started, of course. But yeah, yes, durability is important.
Yeah, and there's a great question here, which I think is a fundamental one in everybody's remarks. Is it's especially for aviation, it's all about weight reduction, improving the power density. So actually, Pat Sarnaki's put it better than I could. He's asked, what are the bottlenecks in reducing weight of fuel cells? So kind of we touched on a few of them, but what are the real challenges, things that are holding us up right now in getting the weight down so that it can support larger aircraft and really progress in the aviation field?
I mean, higher temperature operation is going to bring the weight down. I mean, that's big, right? So being able to drive, like you were talking about earlier, is driving the temperature higher and higher is going to help reduce the weight of the balance plant. That's a big deal. I think the plate technology, reducing the weight in the plates themselves, which is a significant part of the stacks, is another piece. I know that we're looking at and have done a bunch of work in already to reduce the weight there. I think those are two big areas that I would look at. But you can also look at the MEA and start reducing the mass of the MEA components as well.
Yeah, and I think I'll step in for a second there. Not to repeat too much of what Meryl said. The balance of plant in general, right, is today's. If you look at the fuel cell systems, the balance of plant is typically heavier than the stacks themselves, and a lot of that can be improved quite a lot. So we, for example, on our side, for even the first engine introduction, we've developed our own compressor for the 600 kilowatt operation that is linked directly to the rotating shaft, basically, that you always have a constant speed shaft effectively in the aircraft, and you can offtake power if you do proper management of the flow for the compressor, which we do with variable vanes. So if we're now qualifying that, and that has quite significant savings both on the weight side, but also on the certifiability side. It's a simpler components than a typical 100,000 RPM or 120,000 RPM electrical compressor driven by the high-speed inverter with all the software technology and all that, right? So balance of plant improvements are quite significant. One of the other bits that we're looking at is higher integration, even in the stack. How we can, instead of having 7 or 8 layers of with every cell, can we can we make things more structurally solidly integrated so that we need less of a supporting structure for the stack? Because as you grow the size of the stacks, both in terms of the cell count and the cell size, the mechanical stability, especially in the vibration environments, becomes a little bit of a problem. Looking at the cell design is interesting as well. So we have some efforts there as well.
Fantastic. Another thing that's cropping up quite a lot in the chat is we've got quite a few fans of solid oxide in there, throwing in their thoughts as to why not solid oxide instead of HDPEM as a pathway. So I just wondered if, Val, Merrill, any thoughts on whether solid oxide fuel cells ever have a future as an aviation power generation technology?
That's a great question, and I don't have a good answer for you on solid oxide fuel cells because I've been primarily focused on PEM. So I don't know, Lisa, if you can help out with that one.
No, I don't know too much, but what I understand is that it might be larger solutions, and also maybe the startup and transient times are a bit different. But somebody needs to help me out here also.
Yeah, and also
Got a PEM panel here then.
Yeah. Not pretending to be an expert, but we of course, as an integrator as well, we've looked at various technologies, and granted, the opinion is formed based on the current state of technology and the currently available roadmaps, but some of the structural sort of robustness is a question, right? Putting it in mobile environments, especially with high stress levels, where you need to certify to a certain number of Gs on impacts and things like that, becomes a little bit of a problem. Weight was traditionally not a great attribute for solid oxide fuel cells. Then also, in addition to the times, as Lisa mentioned, the efficiency in the in the sort of stationary applications tends to be high because of the additional sort of combined cycle type approaches, which are hardly going to be possible in the constrained aviation environments, in again mobile environments on the aircraft. So I think there are significant challenges on this. So I think for the next couple of generations, probably we're looking at more advanced PEM cells with higher and higher temperatures.
Yeah, I think there was a good comment just there in the chat, if I can see it again, from Dr. Wasim. He was talking about the complex architectures and generally quite heavy components, so perhaps not the optimal solution in this context. So our next panel actually is going to be looking specifically at liquid hydrogen systems for storage, because thinking about how you improve the volumetric energy density moving up to larger aircraft sizes. So it's more on the storage side, but I'm just curious to see if this panel has any thoughts about what the impact of having liquid hydrogen on board an aircraft might have on the fuel cell system design. And are there any major impacts from changing the source of fuel from gaseous to liquid?
It's a good question.
As long as it's gaseous hydrogen entering the system, I'm happy.
You're going to have something that converts the liquid to gas on the system. So that'll add weight, and it depends on what that weight's going to be. But your liquid storage is going to provide you a higher density of the liquid on board. So that's a positive thing. You're going to need liquid storage, but you're going to have to be able to convert that to gas to get into the fuel cell. And we'd have to be looking at all of that. Yes.
Yeah. From the system perspective, as of course, you have a potential cold sink with any cryo storage, whether it's liquid or cryocompressed or just chilled gas that you could use for to offset your thermal loads. So that can potentially reduce the weight of the overall system, right? Now, unfortunately, we've done the calculations, and I'm sure a lot of this group has done as well. But it seems that relatively small fraction can be offset through that. But nonetheless, even if you kind of set 10 to 15% of your thermal loads, you can still reduce the system.
Perfect. And we've got a question as well here about from an anonymous attendee looking at the fundamental physical and chemical limitations specifically of HDPEM systems. But I think we could probably broaden that out. So I suppose it's a question about, we talked about power density increases. I think Val gave some potential target figures. But what are there natural limits that you see to fuel cell power density that preclude certain applications? Or I'm just curious as to where you think the line is drawn.
Let's
go to Lisa first on that question.
Sorry, we talked about this the other day, actually, looking at each other and the team here at PowerCell, and thought, what is the limit? And I don't think we know the limit yet. The important thing is to make sure that you can design a new cell design, more or less, with a stability cell to cell variation, but also over the cell that is enough equal to be able to scale it up in different dimensions. But also to work, of course, on the materials and improvements, catalyst wise and membrane wise. But the most important thing is to make sure that you have a flow spread that works with your cell design. And yeah, sky's the limit. I don't know.
Yeah, I don't like the thought of putting limits on a technology, because you can have a breakthrough at any time. You know, if you set your sights on a limit, like only being able to run, 6-minute miles, and as soon as somebody hits that 5-minute mile, they break through the window, and all of a sudden the impossible is possible for everybody in the marketplace. So I don't want to say that we can put a limit on it. I don't want to say there's a limit on the technology, personally.
Yeah, I love it how you put it, Meryl. And I'll take it from the other end. I think we do know that it's possible to get system level specific power and power density to the levels of at least medium-sized turbines, which is 3 to 4 kilowatt per kilogram. And I'm talking system level, right? So getting gross power output out of the fuel cells. We're not there yet collectively, I think, anybody, but we, I think, all know that it's possible to get that, right? So I don't know where the limit is, but from practical standpoint, when we get to that 3 to 4 kilowatt per kilogram at the system level, we're as good as the turbines on the weight basis, right? And that's a huge milestone.
Brilliant. Okay, so we're running up on time, so we're about ready to wrap up. But I want to kind of sign off with one final question, one final answer from all of you. But what are you expecting to see next year? What do you think? What kind of positive? What are you hoping to see next year in fuel cell development? Do you have any big targets or aspirations? And are you optimistic about fuel cell development in aviation? So Meryl, let's go to you first.
Well, of course, we're optimistic about fuel cell applications in aviation. That's an easy question. There's a lot of potential there. So there's no doubt about that. What do we hope to see in the next year? A higher current density and lower weight for our design are some big, and those would be the two big things for me that we have on our roadmap.
Lisa?
Okay. Yes. The first target I had in mind is that we will build our first stack for this new generation around summertime next year. Really exciting that will be really exciting. It's within this aviation European funded newborn project. What more? Yeah, we have at the moment, I think we have 18 projects running in parallel in the aviation area. So hopefully a lot of good things will happen. Yeah.
So a lot for us to report back on next year. But Val, anything from you?
Lots of flying hardware. That's what we need exactly. So on our side, of course, we're, as I mentioned, submitting the design of the first engine to the authorities, and we're going to go through the initial certification and qualification tests, ground and flights next year for this ZA600 engine, 600 kilowatt engine, as we call it. That's going to be pretty exciting, and we're quite confident that we're going to go through that process quite efficiently. And then the second thing that's going to happen is, which we're pretty excited about, is the first manned flight of the high temperature fuel cell system. So that's happening next year as well.
Superb. And with that, I want to say thank you to our panelists. Thanks, Meryl. Thank you, Lisa, and thank you to Val. We're going to take a really short break. We'll be back on at 5 p.m. sharp, so 3 minutes or so to grab a cup of tea. And then we'll be back to talk a little bit about liquid hydrogen at the top of the hour.
Yeah, thanks so much for having us.
Thanks,
Thank you.
Thank you.